First of all, I would like to thank you for the invitation and the opportunity to present some findings on this topic. I would like to use the introduction to the topic to present basic findings on the behavior of the BLC during and as a result of strength training loads. Various studies examined the influence of variations of load parameters in resistance training on metabolic stress parameters, such as blood lactate concentrations. For example, sequence of small and large muscle, effect of load and time under tension, effect of exercise protocol, for example, strength versus hypertrophy versus muscle endurance, and effects of exercise and muscle percentage or dependence of number of sets and muscle volume. This slide shows BLC curves from various studies clearly showing the metabolic stress as measured by BLC rises strongly as a result of even one set of exercise. This then accumulates over the next few sets and show a similar pattern to a cycle sprint. Most studies show the maximal afterload lactate or simple course of blood lactate during and after the session. But no study determined the parameters of lactate kinetics or activation of glycolysis via vLamax in resistance training. In this context, we have conducted various studies in recent years that show initial findings on the behavior of vLamax during local strength loading and resistance training. The primary aim is to test the extent to which this metabolic parameter is suitable for demonstrating adaptations in energy metabolism as a result of resistance training. First of all, I would like to briefly describe the method we are using to determine the maximum lactate accumulation rate in strength training loads. The red boxes, the studies in the red boxes I will present. We use an isokinetic strength test based on the isokinetic cycle sprint. This means the fixed speed of movement. This involves performing one-legged flexing and extension movements with maximum possible power. Capillary blood samples were taken before and immediately afterwards. Depending on the test objective, this was done up to the maximum of 30 minutes after the exercise. To determine the fictional lactic time interval, we used different methods. For this example, the repetition after the maximum output had been reduced by 3.5% was used. The BLCs was fitting with a Bateman function. This function is suitable to calculate the constants of kinetic in two compartments, here muscle and blood. The first study compared the lactate accumulation rate between isokinetic cycling sprint and isokinetic strength test. The background is that adaptations in anaerobic performance following the resistance training interventions are usually described as change in jumping power or fatigue resistance. These variables only allow indirect conclusions to be drawn about metabolic adaptations. This study therefore initially examined the difference between a cycle sprint and strength test with regarding to vLamax. 14 trained male subjects completed an isokinetic strength test and a cycle sprint test on different days. The single leg strength test includes 10 maximum extensions and flexion movements as described above. The speed of movement was 180 degrees per second. The cycling sprint test lasted 15 seconds and was carried out at 130 revolutions per minute. The resulting average test time was comparable between two tests. In the strength test, nearly 16 seconds. In both tests, capillary blood samples were taken before, immediately at the end of the test, and up to the 9th minute after exercise to determine lactate levels. The vLamax was estimated as described above, according to Marder, in 1994, where the TLAC was determined using a performance-based method. Described also above, we used the time point at which the peak power had dropped by 3.5%. The results showed clear differences in the BLCs between two tests. This is due to the different proportions of muscle used in each test. In the cycle sprint, it's assumed that approximately 40% of the muscle is active, and in the strength test, 25%. The peak power showed a very high correlation between two tests by 0.94, while the absolute vLamax differed significantly between two tests. The vLamax in relation to the walking muscle was comparable. Although there was a moderate correlation of vLamax between the two tests, a high deviation assumed to the relatively high standard error of estimation of 0.22 millimole per liter per second. Based on this result, a prediction of the test result of a strength test cannot be made with a cycle sprint test. The next study calls reproducibility of blood lactate concentration rate under isokinetic force loads. Few studies investigated reliability, reproducibility, or variability of vLamax in all tests with cycling, running, and rowing. For example, Harnisch, Meixner, Held, and Quitman. The ECCs ranged from 0.47 to 0.91 across all test forms. A study by Wawa suggests lower reliability with increasing test time. In this study, the reproducibility and variability of the vLamax was investigated during single leg force loads. We examined two groups of male subjects who were all experienced in strength training. Group 1 performed 8 single leg flexions and extension movements on an isokinetic strength testing device. Group 2 completed 16 repetitions. The participants in each group performed 2 tests in a test-retest design with an interval of at least 24 hours. The movement speed was carried out at 210 degrees per second. This results in an exercise time of nearly 12 seconds for group 1 and 23 seconds for group 2. The performance values showed a high correlation between 0.7 and 0.98 in both groups. Group 1 with 8 repetitions showed a higher correlation. The vLamax of group 1 showed a correlation between both tests by an R 0.72. In group 2, there was a correlation of an R by 0.67. This can be considered a high linear correlation. The plot in the left shows the difference of the test with 8 repetitions and the right of the 16 repetitions. Furthermore, the test differences showed homoscedasticity. The measurement error was 0.04 millimole per liter per seconds in both groups. The limits of agreement were found to be 0.11 millimole per liter per second. The data suggests that single leg isokinetic strength test to determine the vLamax is a reliable possible. The next study is addressed to a training intervention and cause adaptation of maximal glycolysis rate after resistance exercise with different volume load. There are currently few studies that have investigated changes in vLamax as a result of training intervention. One example is the study by Hommel at the year 2015, which showed only habituation effects as a result of sprinting interval training, but no real adaptations, which would have been expected. Many studies investigated adaptations in muscle protein content, glycolytic enzymes, or muscle size through resistance training. For example, Hauen at the year 2019. Based on the increases in glycolytic enzymes after 6 weeks of resistance training, it could be assumed that this should also be reflected in an increase in vLamax. 24 subjects completed a one-legged maximal strength test with 10 repetitions at 180 degrees per second. Capillary blood samples were also taken to determine the lactate concentration before and after the test. The estimation of vLamax was based on the difference between pre-exercise lactate and maximum concentration in the post-exercise period and the test time with subtraction of T-ALAC. After the test, the subjects were assigned into training groups with different exercise protocols. Protocol 1 involves an high volume, low load training. This group completed each set to the maximum of possible repetitions. Protocol 2 had a low volume, high load training with 10 reps by an intensity of 1 repetition, 70%. Both protocols had 3 training sessions per week with 3 exercises for the lower extremity, such leg press, leg extension, and leg curl. 5 sets of 10 repetitions were performed on each exercise. The training load was determined using 1 repetition and repeated at 2 week intervals. This was indeed to adapt the intensity to the specific protocol over the 6 weeks. After the intervention period, a further measure of vLamax was carried out using this isokinetic strength test. At first, both groups showed significant increases in performance in the isokinetic strength test. Significant time effect of vLamax was observed after 6 weeks of strength training. In the high volume, low load protocol, vLamax increased significantly, but in the low volume, high load protocol, the increase of vLamax was not significant. In addition, a significant correlation between delta vLamax and delta power max was found across all subjects. It should be noted that resistance training can be increased vLamax. Presumably, resistance training with high volume and medium loads is favorable to increase glycolytic activity. Increases in power output are associated with increases in glycolytic activity. Future studies should investigate how differentiated protocols differ in the adaptation of vLamax. Thank you for your attention.
Thank you very much, Nico. That was really interesting. It's really nice to be able to see some training studies starting to come out in the field of vLamax. I think it's going to be really vital going forward. So on that sort of trend going forward then, what do you think needs to be done going forward for training studies? What would you recommend researchers do from your previous experience in conducting training studies within the vLamax field then?
Also this study was example with a wide range of exercise variables, exercise parameters like load or repetitions. I think the following studies should examine differentiated protocols with smaller steps between intensity or exercise volume. And I think it's also interest we look to the adaptation over the time, not in a pre-post design, but with a test series 2 weeks or 3 weeks for a longer intervention time. Then we can better understand the kinetic, the adaptation kinetic for vLamax through resistance training. Better will also we can combine this with muscle biopsy observations.
Mm-hmm. What do you think the optimal duration for a training study to see significant adaptations in vLamax is then for this sort of population?
We have orientated on the study by Hauen. They have 6 weeks intervention and have shown a significant change in the protein content and enzymes for glycolysis like PFK, or enzymes for the citrat cyclus like citrat synthase. This was down-regulated, PFK was up-regulated. That's indicate in the change in the glycolysis. That's for 6 weeks, but I think longer periods with this test series after 2 or 3 weeks were necessary.
Mm-hmm. Excellent. Do you think volume of muscle body plays a big role in adaptations over the training? So if we were to look at upper body resistance training, do we think that it would take longer to see these adaptations or not?
It's a complicated question. The glycolytic content is associated with muscle volume or muscle fiber size.
Mm-hmm.
I think this is a relationship, for an untrained population. The first step would more an glycolytic adaptation sign with lower muscle volume, but in the time this will similar change, and the adaptations in the upper body that can I not really unswear today. I think it's between upper and lower body, the muscles are differentiated in muscle fiber content, and the changes are also different over the time.
Yeah, excellent. Excellent. So I think Hennon's got a question as well. So do you think the increase in vLamax after resistance training is the muscle becoming more glycolytic, or just as a result of muscle hypertrophy? I think you kind of alluded to that in that previous statement, really.
I think more glycolytic enzymes by more muscle mass, but it's produced by the specific exercise protocol. When I do an strength training protocol with repetitions 1 to 5, that's not the enzyme content for the glycolytic. When I do a protocol with more repetitions, example 8 to 20, that's more an enzyme adaptation, and also an muscle mass adaptation. So I think.
Yep, excellent. Thank you very much.